Okay, so simple harmonic motion. Yes, you have this sinusoidal wave you'll see all over the place, and it's definitely related to waves. Essentially, as it says, oscillations, it's when something is oscillating, in other words, moving back and forth. So it could be a pendulum moving back and forth like this. It could be this ball is being rolled down a slope and it goes past the midway point, builds, slows down, eventually gets to the right hand side and then goes back again. So it goes back and forth, back and forth. All the time, if you were to plot its position against time, you get a graph like this. Also, if you plotted its speed against time, or velocity against time anyway, if you plotted its velocity against time, you'd get a graph like this. And also, if you plotted its acceleration against time, you'd also get a graph that looks similar to that. Distant or displacement, as in position, with the midway point being 0, the position, the against time, the velocity against time, and the acceleration against time all produce a graph that looks similar to this, or not identical, so it could look more like a cos graph, or maybe, well, it actually won't look like a cos graph, but it'll look like this. I can't quite remember now, actually, but maybe like a cos graph. Anyway, it'll look like a sort of wavy graph like that all the time. So let's try to identify what is it about any simple harmonic motion system where they all have in common. And this is what I'm about to explain here, is probably the most important things you need to understand about simple harmonic motion. So let's take this pendulum here, the same, and I'm going to apply it to the maximum spring as well in a moment. But we've got positions. Let's say position 1. Let's write in black. It's going to start off at position 1. It's going to move towards the left. The midway point would be position 2. It's going to carry on past the midway point to position 3, which is the most extreme position on the right-hand side. We could call that the amplitude. And then once it reaches the maximum point on the right-hand side, it's going to start to come back to the middle point. So the middle point, therefore, would be now position 4, as well as position 2, and then finally back to the original point, which we call position 5. Then the whole thing repeats. So it goes back and forth, back and forth. Now, if we call this, if we say that A is the value of the, actually, let's. Okay, I'm just going to pause this and set up a little table. So we've got this table here that we're going to fill in a moment. Let's give it a bit of colour. What we're going to be thinking about is what direction, what size and direction are the displacements, the velocity, and the acceleration at each position: 1, 2, 3, 4, and 5. Okay, so those are the different points of an individual oscillation as it moves forward to the right and back again. We're going to use standard convention of right is positive and left is negative. So right is positive. And we're going to just use words like max and minimum or 0, okay? Or if you want medium. So for example, if you think it's got the maximum velocity and it's going to the right, then you would say plus max. If it's maximum velocity to the left, you'd say minus max. And if it's 0, you say minus. You could just put 0 and so on, medium, and so on. So I'll pause this and we'll see if we can fill it out. So here's the table filled out, and I've color-coded it. We can see the negative maxes and the positive maxes and the zeros. So at the position 1, it's not started moving yet, but it's at the most extreme position on the left. So it's got a negative max displacement, 0 velocity, but it is about to accelerate. It's got I guess you could say the force is at the maximum, so the acceleration is going to be at the maximum towards the right. Okay, as it reaches the middle point, position 2, the displacement is now 0, goes back at the middle point, the velocity would be at its maximum. It would have got faster and faster and faster and faster, and then as it goes past position 2, it gets slower and slower and slower until at position 3 it's 0. Also at position 2, the acceleration is 0 because the acceleration there's no force, is there? There's no force pulling it left or right at position 2, and so there's no acceleration. So what we want to realise then, and this is the most important part about simple harmonic motion, I suppose, is that wherever the displacement is maximum, the acceleration is maximum, but in the opposite direction. Wherever the acceleration, wherever the displacement is maximum, the acceleration is maximum, but in the opposite direction. That is the most important thing. And so whenever you have a system that is in simple harmonic motion, the acceleration is actually directly proportional to the negative of the displacement. This is the thing that whenever we want to find out is a system in simple harmonic motion, we want to find out whether or not that's the case. If it is the case, the system is in simple harmonic motion. So in other words, as it's pulled more extremely to one direction, the acceleration increases. As I double the distance from the equilibrium point, I double the acceleration, but in the opposite direction. And on vice versa on the other side, if I pull it more extreme to the other side, the greater I pull it to the one side, the greater the acceleration is. But actually, it's directly proportional. If I were to double the distance from the equilibrium point, I double the acceleration, but in the opposite direction. The more it pulls off to the right, the more the acceleration is moving towards, it's acting towards the left. So whenever you pull it to one side, the acceleration is always pulling it back towards the equilibrium point, and the more you change the proportion by which you change the position is the same as the proportion of the acceleration, but in the opposite direction. So this is the most important point.